How will AI change electric power? Welcome. My name is Alex Pavlak. I'm a PhD engineer from Severna Park, Maryland, and chair of the Future of Energy Initiative. We are an ad hoc group of accomplished engineers focused on facilitating the clean energy transition. For the past 18 months, my focus has been on how to power AI. This presentation summarizes the results of a concept study. The full report is available for download. In systems engineering, a concept study explores options. Starting with a blank sheet of paper, what do the fundamentals teach us about how the pieces naturally fit together? Don't sweat the small stuff, keep it simple. The study's central finding is clear. We will not have one integrated power system. Instead, two separate architectures will emerge because that configuration is simpler and cheaper for everyone. One system will be a refined version of today's grid. The other system will be massive, off-the-grid AI campuses, gigawatt-scale computers co-located with generation that does not load the grid. This is the 2050 vision. Now let's see how we got there. Neural network AI is delivering impressive products. The potential is real. Neural nets gained attention in the 1980s when Geoffrey Hinton figured out how to train them. But at the time, they could not compete with symbolic AI due to limited computing power. The enabling technology is massively parallel processor chips. This technology, originally developed for video games, is now being applied to neural networks. Training a neural network requires high-density infrastructure. The whole brain needs to be trained at once. Neural network AI presents electric power with two new system requirements. The first is concentrated loads, far larger than what the grid normally services. The second is uninterrupted electricity, a quality greater than what the grid normally provides. Let's review the legacy system. The grid is the product of 140 years of evolution. It has thousands of independent generators serving millions of widely distributed small loads. The sophistication lies in balancing supply and demand at scale through markets that adjust every 5 minutes. That's an impressive achievement. Today's legacy system does not have very large loads. Big facilities like chemical plants find it simpler and cheaper to generate their own power rather than to rely on the grid. This is a hot clue about the future of AI power. Now let's look at cost drivers. Two components, generation and transmission, dominate electric power cost. In PJM, a 13-state regional system operator, 65% of its cost is paid to generators to produce electricity. 35% is paid to transmission owners to deliver it to local utilities. A data center that plugs into a high voltage system should pay a price that is roughly equal to the PJM wholesale cost. It is important to note that the transmission cost is a capacity cost determined by peak demand, not total consumption. Whether the power line is used continuously or only rarely, the annual cost will be roughly the same. An off-the-grid campus eliminates transmission cost and its associated failure modes. Base power costs are about 35% lower than grid-connected configuration. Reliability improves. Isolated systems are not vulnerable to grid-wise outages. An off-the-grid campus also enables the integration of power generation and computing operations. This includes shared cooling systems, coordinated maintenance. We can incorporate high-temperature thermal storage in the power block to eliminate batteries and backup diesel. And DC generators could eliminate AC-DC inverters, conversion losses, and failure modes. These development opportunities were not considered in the current vision statement. We have a credible and consistent cost database out to 2050. The concept study evaluates 26 scenarios with a 5 nines availability goal. Key points are AI campuses should not load the legacy grid. They may sell excess power, but that's a secondary business. Campuses will rely on multiple independent generators for high availability. Co-locating computing and generation provide substantial integration opportunities. Small modular reactors are likely to be the preferred generation technology. Cooling will be a strong factor in site selection. Expect facilities to cluster near abundant water. There are many pathways to 2050, so strategic planning and stage development will be valuable. Finally, a policy caution. Beware of price wars. AI can pay generators more for electricity than the legacy grid cost. This could destabilize legacy markets. Policymakers must protect the integrity of the legacy system. This concludes the executive summary. The full concept study is available for download at futureofenergyyinitiative.org/pubs with a capital P /59s.pdf. I thank you for your time.